Okay, so this video, it's going to be a more conceptual video. I'm going to go a little bit fast, so if you find that I am going too fast, what you can do is you could always watch it again. Or what you could do is you could always, if you feel like I'm going too fast and you missed a point, you could always pause and then rewind, rewind, and then watch again. So that's the beauty of these digital lessons, that you have some sense of control over the instruction, right? If I'm going too fast, then pause, rewind, watch again. I'm still going too fast. Oh, you didn't quite get the last little bit of what I said. Pause, rewind, watch again. Right? You could repeat. You could repeat this again and again and again. Really, sometimes that's really the best way to learn. So I will be going relatively fast. That's a little bit of a warning there. And again, this is going to be a more conceptual video, maybe more conceptual for review, because what I am finding is that there is still sometimes a lack of understanding of some of the basics, or some of the fundamentals, of graphing, and some of the fundamentals of looking at relations in general, right? Relations between maybe two different measurements. So, for example, if we have two different measurements, let's say I have a measurement of position, and let's say I have a measurement of time. Well, position and time, they relate, right? They relate to each other. For example, position and time relate to each other in this wonderful thing that we call motion. So we're gonna look at motion as sort of our example to investigate the fundamentals of graphing and relations. So a simple example of motion, right? Motion is essentially where position simply changes as time changes, right? As a clock ticks, your position changes. If you are in a car, that's my wonderful car, then and if the car is moving, if the car is in motion, then over some set period of time, if you are initially at position A, eventually you will maybe be at position B, right? You will move, right? So that's essentially what motion is. Motion is just where position changes with time. And if position changes a lot with respect to time, then you're moving faster. If position changes only a little bit with respect to time, then you're moving slow. So that's what motion is. If you are not changing your position as time changes, then there's no motion, right? So you're standing still. So let's say you are running. So here you are running, and let's keep this whole position A, position B sort of framework. So here you're happy to be running. Yay, you are free. And let's say that at position A, you've really only just started running at that instant in time. So let's say time is 0 here. And if time is 0 here, and you've just started, we could say that it would be really simple to call this 0 meters of distance that you've moved, right? So after a certain amount of time, you might be at some other position B. Maybe that amount of time is 2 seconds. And maybe after those 2 seconds, you are now at a new position. You are at 4 meters of distance relative to position A. So here you are, you are happy to be running still, and it took you 2 seconds, but eventually your position changed. Your position changed by 4 meters. And then you could continue running, right? You could continue running, and maybe at this point you're at what we could call position C. Maybe a total of 5 seconds has elapsed here, and then you are, let's say after these 5 seconds, you are now at a position 10 meters away from your original position here. So here you are. And this is just sort of a diagram of your motion, right? Keeping track of time and position at different moments in time, and looking at how time corresponds to position at all of these different points, A, B, and C. So what we can do is we can keep track of all of the time values, right? Because it's not like all of a sudden you are at position 0 at time 0 here, and then you count 2 seconds, and then all of a sudden, blip, at exactly 2 seconds, you all of a sudden appear at position B, and then you stay at position B for 3 more seconds, and then all of a sudden, blip, you are at position C. That's not the way it is. Time moves continuously, not in these sort of blips, right? So after time 0, you are traveling and traveling and traveling and traveling at all of these points in time between 0 and 2, right? So you're traveling at all these points in time in between t equals 0 and t equals 2. And then in between t equals 2 and t equals 5, you're traveling at all of these different points in time as well, in this sort of continuous, stream of milliseconds or nanoseconds, or you can go as small as you like for time here. But the point is that it is a continuous stream of time that it takes to get from position A to B, and it's a continuous stream of time that it takes to get to position B, from position B to position C. So we can keep track of all of these continuous times. So we can keep track of all of the time, these continuous time values, and we can do that on a continuous number line. So number lines are super useful in math. So let's say we have a number line, and this number line moves to the right, meaning as we move to the right, we get more positive. So let's say this is at time 0, and then we can make a scale here of regularly spaced or evenly spaced tick marks to represent 1, 2, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. If it isn't clear that these represent seconds, then you can label this as maybe your time number line that's measured in seconds. So labeling is also another really important thing in math. So here we have a number line, and this number line keeps track of all of the different time values on our number line, right? Sometimes we are at one instant in time, we are at t equals 0. At another instant in time, we are at t equals 2. And another instant in time, we are at t equals 5 seconds. And of course, to go from t equals 0 to t equals 2, we have to travel through all of the values in between t equals 0 and t equals 2. And to get from t equals 2 to t equals 5, we have to travel in time, through all of these continuous values to go from t equals 2 to t equals 5. And it might seem kind of silly to be that specific and to be that explicit about the fact that there are really a continuous stream of values in between these time points, in between these instants. But it's actually very important in math that we are explicit about this. And not only that, we can also, and let's do this in a different color, we can also keep track of all of the position values, right? You're at different positions at different moments in time, so we can keep track of all of the different position values on a number line as well. So we can just draw a relatively straight line. So here's a relatively straight line. And let's label what this line represents. It represents position, and we often represent position with d, which sometimes we could say means distance, or sometimes we could mean displacement. And let's say we are traveling and measuring our position or distance in meters. So let's be explicit about that. Units are important as well. And we can make a series of tick marks and a set of evenly spaced marks. So 1, 2. So this is 0. It's always good to start at 0. Not always, but usually it's good to start at 0 as a reference position. So here's our starting position at 0. And then we go from 0 to 1 to 2 to 3 to position 4 meters, 5, 6, 7, 8, 9, and 10. So, and it's good as well to label these tick marks so that somebody who's reading your number line knows what one tick mark represents. Because it could be that for some reason you choose one tick mark to mean 5 meters, and then it will go up by 0, 5, 10, 15, 20, right? But that's not necessarily what we're going to do. In this example, we're just going to go up by ones. So we'll count 1, 2, 3, 4, 5. So here it's clear that every single jump to every new tick mark represents a jump in terms of 1 meter, right? Because it takes 5 of these tick marks to go 5 meters. So anyways, that's clearly labeled. I went up to 10 meters. Now here, it's actually really useful to represent all of these different possible positions on this continuous stream of numbers, which is a number line. What we are truly interested in when we talk about motion, what we're truly interested in is looking at how time and position correspond, right? How they're related to each other. Right? How do time and position correspond with each other? How do they relate? Right? Remember, this is really a chapter called linear relations. So we're looking at how different measurements or different quantities, we're looking at how they are related to each other. So really what we're interested in, if we're interested in motion, is we're interested in how in the relationship between time and position, or you could say more fancifully, you could say we're interested in the correspondence or the relationship between time and space, right? Position is really different points in space. So we can look at how time and position correspond, and one way to do that is by connecting the time values. So we can connect the time values that go with their particular position values. So how can we connect them? One ineffective way to connect them, I'll show you. And then from that sort of less effective way, what we're going to do is we're going to modify it to make a much more successful method for connecting time and position values and seeing how they relate or seeing how they correspond. So let's draw our time axis. Our time axis is in blue. Our time number line is in blue. So here I have my time number line, measuring time in seconds. And here is 0. And then 1, 2, 3, 4, 5. So that's 5 seconds. And then in my red number line, here I have my position axis or position number line, measuring it in meters, starting at 0 and then going from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that represents 10. This represents 5. So we can look at how time and position correspond by, again, like I said, connecting the time values that go with or correspond with their particular position values. So, for example, we know that when time is 0, we know that the corresponding distance is, or position is 0, right? When at position A, if I scroll up just for a brief moment here, at position A, I might notice that the instant that I start, I am actually at 0 meters of distance away from my original position. So t equals 0 should correspond with d equals 0. Another way that I can do this is I can notice that when I have been running for 2 seconds, I am at position 4. I am 4 meters away from my original position. So at t equals 2, I am 4 meters in distance. And let's connect these 2 points. Let's connect these 2 points just to show that they correspond. And I know as well that when I have traveled for 5 seconds, I am now 10 meters away from my original position, right? That is essentially, that is what I am saying at position C, right? When I have been traveling for 5 seconds, I am now 10 meters away from my original position. And let's show that when t equals 5, that corresponds to d equals 10. So those 2 points correspond. So this is one relatively ineffective way to show correspondence between time and position. So one thing that we can notice here, we're going to try to build a more effective diagram to show this correspondence between time and position. So one thing we can do is if we assume that your speed is constant, meaning that meaning that in between points A and points B, you're not suddenly speeding up or slowing down, and in between points B and C, you're not speeding up or slowing down. You're going the same speed between all of these different points. So if we assume that your speed is constant, right, your speed is unchanging in between these values, then we can try anyways to see or to chart all of the correspondences. We can try to see all of the correspondences between time and position by position. It's hard to write and talk at the same time. There's going to be some mistakes for sure. So we can try to find some way of diagramming all of the correspondences between time and position. First, by looking at a pattern. Right? Remember, lesson 1 was really called patterns. So patterns are obviously very, very important in math. So we can look at a pattern that emerges from the information that we already know, from the information that we already measured. Right? Pretend that we were measuring all of this with like some series of meter sticks and a stopwatch or something on your iPhone. So we can look at a pattern that emerges from the information that we already know. So again, we're building here. We're going to be building a system to show all of the correspondences, and to show all of the correspondences, first we should look at the more general pattern that is emerging here. So let's see if we can identify this pattern that is emerging. So for example, we know that if t equals 0, then our position is also at 0 meters. Now there's not much immediately that we can glean from here. So let's now look at the next correspondence here. We know if t equals 2 seconds, d equals 4 meters. Hey, we know that there is a relationship. There's a few relationships that exist between the numbers 2 and 4. So, for example, if we want to look at a pattern, we could say that to get from the number 2 to number 4, we could add 2, or to get from the number 2 to number 4, we could multiply by 2. So there's definitely a few different ways we could go from 2 to 4. But let's look at the next correspondence. If t equals 5, then d equals 10. So we know that to get from 2 to 4, we could either add 2 or we could multiply by 2. But to get from t equals 5 to t equals 10, we definitely cannot add 2 to go from 5 to 10, right? That won't work. We could only multiply by 2. So it looks like the multiplication by 2 is really the only thing that could take us from time to position, right? Multiplying by 2 here will take us from time to position. Multiplying by 2 here will take us from the information for time to the information for position. Will it work for this first example where it was kind of a stranger example? Well, let's see. To get from 0 to 0, you definitely can't add 2, right? That's not going to work. But you could still multiply by 2, right? If you take 0 and you multiply by 2, that'll take you to the next position. So we see that this rule for multiplying by 2, this is really the pattern that emerges. Or another way to say this is if we want our distance information, we can take our time information and we could simply multiply by 2, right? To get our distance information, all we have to do is take our time information and multiply it by 2. So this is our rule. So we could write this as our equation for this pattern that sort of emerges here. Now, from this rule, we can get a lot more information. We could write this equation in words anyways. So we could say the distance is always, and let's be very specific here, the distance in meters, I'm spelling it in the American way for some reason, the distance in meters is always, if it's constant speed, double the time value, and let's be specific again, which time value? Not in minutes, not in hours, in seconds. There we go. So the distance in meters is always double the time value in seconds. That's the pattern. So we could draw some more correspondences here, right? If this is true, if the distance is always double the time value, then when the time value is 1, the distance will be double that. It should be 2. And let's connect those 2 points. They correspond. If the time is 3, then the distance should be double this value of 3. It should be 6. And we can draw that correspondence, right? We can connect those 2 points. If the time value is 4, we could then conclude that the distance value must be double 4. It must be 8. And we could draw the correspondence between those two values. But this is kind of, and we could sort of extend this more if our scale went further, right? We could extend this more. This looks like it would be around 12-ish or something. But really, we can see that this is kind of ineffective. This is kind of ineffective, and it doesn't really get us to our goal of showing the connection between all of the correspondences, right? We have these 2 number lines, and that's great. These number lines show a continuous stream of time values and a continuous stream of distance values, but it doesn't make a continuous connection of their correspondences. And to make a continuous connection, we would have to do a lot, really an infinite amount of calculations, right? We would have to say, okay, at t equals 0.5 here, we could say that the distance value would be 1, and at t equals a quarter here, the distance value would be a half. We can make that correspondence, and we would really just need to do an infinite number of correspondences here, and that is kind of silly, right? We don't have an infinite amount of time, and we can see that it would also, if we were to make all these connections, it would eventually be quite messy. So here is the solution. Here is the big solution to our problem. And this is a solution that is going to be able to allow us to show all of the correspondences between time and position. So here's the solution. The solution is, we're still going to take a time axis, or a number line that represents time values in seconds. Let's say we are at 0 here, and then we can go from, let's actually make this straight. So let's say I have a straight number line here, like so. So here is my time axis in seconds. Here is when time is 0 seconds, and then time is 1, roughly, and then time is 2, roughly, and then time is 3, roughly, and time is 4, and then time is 5. I don't have a ruler. I feel like if I put a ruler on this tablet, I will screw everything up. And we can also look at, so we've drawn our time axis, and we also have a distance axis here. So we also have a distance axis. But instead of writing the distance axis horizontally and comparing them that way, right? Instead of writing the distance axis horizontally, I'm going to draw the distance axis. I'm going to draw the distance axis, and I'm going to draw it perpendicular. I'm going to draw it perpendicular to the time axis. And let's actually move this. Can I move this? I want it to align. Oof. This is part of the difficulty of using these tools here. So I'm just going to draw it freehand. That's relatively straight. So here's my distance axis. So really, the major change that we've experienced here is, I mean, ultimately we have everything else being the same. I have some distance axis, and I can chart some numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oof. Those are. I want to make these as evenly spaced as I can. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's see if we can make this a little bit better. Oh, that's brutal. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. And so I've marked my scale. I know that each jump, each unit rather on this scale represents a jump by 1 meter in position. So I've clearly labeled everything. And what is the advantage? Oh gosh, what is the advantage? I'm making awful work of this. What is the advantage of drawing these axes in a crosswise fashion? What is the advantage? Well, the advantage is that we can show all of the correspondences. I will show you how we can show all of the correspondences. So first of all, we know that when t equals 0, then d equals 0. We can show that correspondence right here. Right, we can show that correspondence right here. We can show that when t equals 2, d equals 4. So when t equals 1, 2, d equals 4 right here. We can also show the correspondence. So here when t equals 2, d equals 4. We can show the correspondence between t equals 5 and d equals 10. Right, so when t equals 5, d equals 10. And we can show where they meet. Where t equals 5 meets with d equals 10, that will be the position C, right? So this is position A, this is position B, this is position C. You could even say, because this is really looking at a correspondence between position and time, or space and time. This is really event A and event B and event C, but we won't bother too much with that. And we know from the pattern of our equation, d equals 2 times t, that the distance is always going to be twice the time. So I could say at t equals 1, d will be equal to 2. So I can chart that position. At d equals 3, t should be equal, at t equals 3, d should be equal to 6. And at t equals 4, d should be double that, right? That's our pattern. Our pattern is that d is double whatever t is. So there we go. So we've charted all of those correspondences, and you might say, hey, I don't necessarily have all of the correspondences in between. Hey, Mr. Peterson, I thought you said we were gonna have a diagram that was able to show all of the correspondences between time and position, right? This doesn't show all of the correspondences between time and position. Well, actually, it does. If you connect all of these points. So if you connect all of these points together, you literally have all of the correspondences between time and position. So there you go. Let's say you keep going and you keep running forever. You could chart out all of the future correspondences between time and position just by following this pattern, right? And you could say, hey, what is this point? Oh, this point is at t equals 5.5. what would the corresponding distance be? The corresponding distance would be 11 meters, right? And so you can find all of those correspondences in between any of these points, right? You can find all of the correspondences in between any of these points. You can find all of the correspondences in between any of these points. And you couldn't really do that here. You would have to have drawn an infinite sort of array. You would have to have drawn an infinite array of correspondences between these two number lines if they were both horizontal or both parallel. But if you make these two number lines perpendicular, then you can literally draw all of the correspondences. That's what this line represents. This line represents all of the correspondences between time and position at any time or any position that you like, right? At any time or any position that you like, all of these correspondences are charted. And another way to really show all of these correspondences we've already done, it's this equation right here. So all of the correspondences between time and position are shown by this graph. And by this equation. Right, so here we have the equation d equals 2 times t. Right, this is the equation. This literally shows all of the correspondences because you could plug in any time t that you like, and then you could find out whatever the corresponding position d would be. Or you can look at this line graph and you can say, oh, at whatever time this happens to be, what would the corresponding position be? Well, the corresponding position would just, if you track it back to this number line for d, it would just be right here, right? At this particular time, you track it all the way up to this line, and when you hit the line, you can see what particular position value you would be at. And this arrow in the bottom left assumes that you didn't really start running at t equals 0. Maybe you were running for a while, so I could maybe get rid of that. Let's say you actually just start at t equals 0. So this is the essence of linear. This is the essence of linear relations, right? This shows the relationship between two different quantities. This is why we have an x-axis that is horizontal, and this is why we have a y-axis that is vertical. It is the best way that we have to show correspondences between two different quantities that are related to each other. So hopefully this was helpful in we really built this up from scratch, right? We really built this up from some sort of really basic situation of motion, right? Just tracking with a stopwatch and a series of meter sticks, different correspondences between time and position of you running between different points, right? And then we noticed that it's really, really useful to keep track of all time, right? Because really there are an infinite number of times that you could track, an infinite stream of times that you could track in between t equals 0 and t equals 1 and t equals 1 and t equals 2, right? You don't suddenly jump from t equals 0 to t equals 2. You have to travel there by traveling through this infinite sort of stream of correspondences. And in terms of space as well, going from position 0 to position, let's say, position 4 or something, to go from position 0 to position 4, you have to travel through all of these different minuscule position values, right, until you get to position 4. And to get to position 10, you have to travel through all of these other position values, right? And so we have these two number lines to describe time and position, and we thought, hey, maybe we could track how they correspond just by writing those number lines next to each other and just seeing how these points correspond. Right? And that is kind of useful, right? It's kind of useful. We see a pattern here that as time moves on, our position moves further and further away from time, right? Because position is always double what the time is. And then we saw that really, if instead of writing these number lines both horizontally, if we write one number line horizontally and the other number line vertically, if we write one number line horizontally and the other number line vertically, then we can actually track all of the correspondences. And that's a very powerful thing. And we will eventually, throughout the years, we will build up from these foundations to into the realm of calculus, where really that's where you really have a really strong understanding of motion, even if motion isn't constant. But hopefully that's helpful to at least look at at sort of the foundations of the meaning of these horizontal and vertical axes and what they are tracking. They're showing you the correspondence between two different kinds of quantities, in this particular case, time and distance, or time and space. Really, this is probably your first introduction into what's technically called a space-time diagram. A space-time diagram. So you can impress all of your friends with the fact that you know what a space-time diagram is. Usually in high school we call this a position time diagram, but eventually if you go into physics, you will start to generalize this into a space-time diagram, which is when you go into learning about special relativity and what Albert Einstein was sort of always talking about. Another thing that we can notice here actually is that this particular line, it has a particular slope. So this particular line has a slope. And so we could say the slope is the m value, right? So this particular, and another way of saying this is this particular line has a steepness, right? It has an incline to it. So this particular line has a slope. It is what we usually call the m value. We know that the m value is really just the number that is in front of what we usually call our independent variable here. So here our slope is really 2. So our m value is 2 here. And what does our slope represent in this particular case? Well, the slope is really just the rise over the run. What is the rise charting? Well, the rise is charting some difference. The rise is charting some difference in y values or position values. So distance. And what is the run charting? Well, the run is charting some change in your x values, or in this particular case, our time values. So the run is really just a difference in time values. And when we divide distance by time, really that's a formula for speed. So this is another advantage of graphing all of these correspondences like this, is that if we are able to calculate the slope, if we're able to calculate the rise over run of some sort of distance versus time graph, or position versus time graph, we can get the speed as well, right? And what is the speed? 2. 2, the speed here is 2. And what is our distance unit? Meters. What is our time unit? Seconds. So the speed here is 2 meters per second. So one advantage of graphing the relationship between position and time here, one further advantage of graphing the relationship between position and time, is that we can pull more information from that by looking at how time and distance relate, and that gives us, ultimately, more information like speed. And eventually, you'll be able to pull even more information from this, like something like acceleration, and so on and so forth. So there you go. Hopefully, it's helpful to build up the sort of foundations of this unit from scratch. I hope this makes a little bit more sense. If you were confused about it, maybe I confused you further. If I did, hopefully you just forget about this whole video. But really, this is sort of the logic that builds up these diagrams to be exactly the way that they are. So hopefully that's helpful, and I will see you in the next video.